All right, 6.2 part 3. I want to show you how to do integrals in your calculator here. So in order to do this in a calculator, this is the notation. So if you have some integral from a to b of f of x dx, in your calculator you're gonna put in n int. I'll show you that command in there in a second. You're gonna type in the function comma x, because you have to tell it what variable you're integrating with respect to. Then you're going to put in a and b, that's the lower and the upper bound in that order, and that will compute the integral for you. So let's just do an example of that real quick. Suppose that we are looking at f of x equals sine of x on the interval from 0 to pi. Whoops. Close the interval from 0 to pi. In our calculator, we can figure that out. We're going to hit math, and we're going to arrow down to n int, fn int, and we're going to type in the function, so sine of x, whoops. Then we got to tell what variable to use, x. So you could do this with t. If your function was in terms of t, you could do sine of t, comma t. And then we're going to do comma 0, comma pi, like that. Hit enter. And then we'll get the approximation, and now I'm wondering, I'm in degree mode, sorry. Try that again. 2. Okay, so there he is, 2. It's the same value from that exploration. So there you go. That's how you do that in your graphing calculator. I'll show you in Desmos real quick as well. So for Desmos, I should have already had this graph up, but anyway, for Desmos, you are going to do the integral command. It's sort of nice. It brings up an integral symbol. So if you just type int, it will bring it up, or I believe if you go over to functions, miscellaneous, you can see the integral symbol there in the lower right, or lower left of that box. We can put in 0 to pi, and then sine of x dx, and there you go. The TI-84 pluses and newer calculators will bring up this math type notation. So you put in the upper and the lower bound, and then you need to put in the function and then the variable x, or whatever variable you're using. So that's how you do it in Desmos or a graphing calculator. Excuse me. So that's that piece. Let's go on and talk about the very last thing in this section, and I'm sure that you're all happy that we're finally at the end. We're going to talk about discontinuous function integration. So discontinuous function integration. Now, when I did the proof, I'm not sure if I made a big deal about it. I don't think I did, if I even mentioned it. But the integral formula works if the function is continuous on the interval that you're trying to compute the integral. If it's not continuous, then you have to do the integration in parts, in pieces. Okay, so for instance, if we had this function or this integral, we're trying to find the integral from -1 to 2 of absolute value of x divided by x with respect to x. That is a curve that is broken. In fact, I'll show you since I've already got Desmos open here. So I've got absolute value of x, and I'm going to divide that by x. This is what that curve looks like. It's got a line at y equals -1 here, and then it jumps to y equals 1. And if I integrate from -1 to 2, well, it's not going to work because there's a discontinuity there. So what I have to do, and we'll sketch this out real quick. So I've got my y and my x-axis. I've got y equals 1 here. This doesn't exist at -1 or 1, or at 0, excuse me, at 0. And so there's my curve. And so if I want to go from -1 to 2, then what I need to do is take and compute this area on its own, and then compute this area on its own. Okay, so I have to break it into pieces. When you compute this, what you end up with is -1 plus 2. So remember, this is below the x-axis, so you get a net area of 1. Very last thing that I want to show you, I just remembered. I didn't have it in my notes, so I'm glad I remembered. that's it for discontinuous function integration. Let me give you the formula right now for total area. Okay, so suppose that you don't want the net area. Okay, and you want a simple way to figure out what the total area covered is. Not the negatives and the positives, so you get the net area, but the total area covered. Here's the process for doing that. You take the integral from a to b of whatever your function is, and you're going to take the absolute value of that function, all with respect to x. Okay, that will give you the total area. And the way that you're going to have to do this is you're going to have to use nint, okay, because we don't have it, unless it's an area that you can recognize and you can use your typical area formulas, all right? And so what we'll do is I want to show you why this works real quick. So let's suppose that I have just sine of x. Let's make it 3 sine of x so it's easier to see. Let's only go on the interval from 0 to pi. No, actually, 2 pi. All right, so there's my, there's what that looks like from 0 to 2 pi. Now, if I wanted the total area covered by this graph, what I would do, or what I should do, is compute the integral. But if I just straight up compute the integral, I'm going to get an area of 0, a net area of 0, because that's what the integral outputs. So in order to fix that, what I'm going to do is take and put the absolute value around the function. So if I do that, hold on a second here. So I can close that function, the absolute value off right there, and you can see that it flips the curve up above the x-axis. All right, so then when you compute the integral, it's only computing the areas of functions, the area between the curve and the x-axis, which is always positive, right? F of x then is always above the x-axis, but it doesn't change the inside of the absolute value. That curve just gets flipped up, all right? And so that's how you find the total area of a curve. And again, you will have to use the calculator on these, unless it happens to be an area that you can compute using other area formulas. And that finally, I think, wraps up section 6.2.